Hey everyone, welcome to the primer video of Wireshark and Go. Let's start with Go introduction. Go or Golang is a programming language that combines the speed and static typing of languages like C with the readability and simplicity of languages like Python. It was first released in 2012 and has gained popularity for its efficiency and developer-friendly features. Some notable differences between Go and other languages include its use of slices for dynamic views into arrays and its explicit error handling, where errors are handled explicitly rather than through exceptions. In Go, slices are dynamic views into arrays. They allow you to work with portions of an array without making a full copy. Here's a quick example. In this example, S is a slice that shares the same underlying storage as the array X. This feature can be quite powerful for working with data efficiently. Now let's talk about error handling in Go. Errors are handled explicitly using the error type. This feature helps us to gather critical information from the error type during the debugging process of program development. Here's an example of how you might handle errors when opening a file. In this snippet, we attempt to open a file, and if an error occurs, we handle it explicitly. This style of error handling is quite different from languages that use exceptions. Moving on to slide 5, we'll build a basic HTTP server in Go programming language. We'll respond to two types of requests, GET and POST. First, when someone sends a GET request to the root path, we'll print Hello World on the web page. In the given code, you'll see that we import the necessary packages including net HTTP. For HTTP handling, we define a function called hello, which takes two parameters, http.responseWriter and http request. The http response writer is used to send the response to client, and http request contains information about the incoming request. Inside the hello function, we use io.writeString to send the hello world message as a response. In the main function, we use http.handlefunc to register the hello function to handle requests at the root path. We start the HTTP server on port 8080 using http.listenandserve. If there's an error, it's logged and the program exits. We define the hello function which writes hello world to http.responseWriter, and this is what's displayed when someone accesses our server. In the main function, we use http.handlefunc to associate the hello function with the root path. This means that any GET request to the server's root path will trigger the hello function. We call log.fatal to start HTTP server on port 8080. If there's an error, it's logged and the program exits. Remember that all the library functions are documented at pkg.go.dev. A good integrated development environment or IDE will show you this documentation inline. Now let's take a look at the code for handling POST requests. In this code snippet, we have defined a new function called submit to handle POST request to the submit endpoint. We use request.parseForm to parse the incoming form data from the request body. This is crucial for extracting data sent via POST requests. Then we loop through the form data using a for loop, printing out each key value pair to the response writer. This is how you can access and process form data sent by the client. Now this is an extended code snippet. We continue from where we left off in slide 8. Here's what we'll be doing with the cookies. We first attempt to retrieve a cookie named submitCount using request.cookie submitCount. If the cookie doesn't exist, we create it with an initial value of 1. If the cookie already exists, we parse its value into an integer. If successful, we increment the count and update the cookie's value. This way, we are keeping track of how many times the submit action has occurred. This is how we handle POST requests, parse form data, and manage cookies in Go web server. In this slide, we have simply reorganized the code to first handle the submit count cookie before processing the form data. This ensures that the cookie logic is executed before anything else. In this slide, we have an even more optimized version of our code. Now our code is even cleaner. We handle the cookie first and then process the form data. Problem solved. In this slide, you can find some extra resources for you to explore and deepen your knowledge on Go. Now let's start with the tutorial on Wireshark. Wireshark is a powerful network protocol analyzer that allows you to inspect the data traveling through your network. It's like peering into the digital bloodstream of the internet. With Wireshark, you can capture and dissect packets to understand network traffic, troubleshoot issues, and enhance network security. Now imagine networking as a well-organized structure with distinct layers, each with its unique purpose. Let's break them down. At the very top, we have application layer. This layer deals with how applications structure data. It includes protocols like DNS, SSH, FTP, HTTP, and these help our applications communicate efficiently. Next, we have transport layer. Here, we are concerned with getting the right service and enduring a reliable stream of data. For this, we have two main protocols, UDP and TCP, both of which are vital for different types of communication. Next, we have network layer, where the focus is getting data to its final destination. The IP protocol takes care of this task, ensuring data packets find their way across the vast network landscape. Link layer is where you get the answer to how we get to the next hop in our journey. For wireless communication, we have cellular and Wi-Fi. For wired connections, we have Ethernet. Finally, the physical layer. Here we have actual physical mediums through which data travels, like radio waves, copper wires, and fiber optics. All these layers work together to ensure data reaches its destination accurately and efficiently. Now let's understand network encapsulation. This concept is fundamental to understanding how data is organized and transmitted across networks. Encapsulation is like delivering a parcel in lots of layers to protect it so that it reaches the destination safely. At the link layer, which is like our first layer of defense, we encapsulate our data with a frame header and frame trailer. These elements help in identifying and protecting the data as it travels from point to point. Within this frame, we have the frame data. The frame data consists of IP header and IP data. As we move up to the network layer, our data is now in the form of IP packet. This IP packet contains the IP header and IP data, which is meant for host-to-host communication. The IP data is further unwrapped as we ascend to the transport layer. Here, it transforms into TCP header and TCP data. The TCP header ensures that the data is reliably delivered from one socket to another. And within the TCP data, we have what we originally sent, an application packet. This application packet belongs to application layer. Now let's take a closer look at the Wireshark screenshot. It's the lower panel. This is where we can dissect the encapsulation process in real network traffic. You see the frame section. This represents the physical layer of our communication. It contains information like frame size. Then we have Ethernet 2 section. Ethernet is a crucial part of our link layer. It specifies how data should be packaged for transmission on the local network. You'll find the source and destination MAC addresses here. Then we have IPv4, which is part of network layer. This is where we add the IP header. It provides essential routing information like source and destination IP addresses. Then there's TCP section representing transport layer. Here we add the TCP header, which ensures that the data is reliably delivered to the correct application on the destination machine. Finally, we approach to the top of the stack, we may encounter TLS, transport layer security, and HTTP2 at the application layer. TLS adds a layer of encryption for secure communication, while HTTP2 represents an application protocol. Now let's see some features of Wireshark that you will use to analyze your PCAP file. First, you have the option to apply filters based on protocol. Wireshark allows us to filter and focus on specific types of traffic such as HTTP, TLS, or any other protocol that you need to investigate. Right here, you'll find the packet list. It's a chronological list of all captured packets showing you when they are received and their source. Parsed packet layers is Wireshark actually dissects each packet and organizes the information by protocol layers, making it easy to dive deep into the details. And the raw packet bytes, this is where you see the actual binary data that makes up the packet, essential for low-level analysis. Now let's dive into how all of this looks in Go. In this slide, we have some Go code that represents TCP layer, Transmission Control Protocol. This code is part of Go packet capturing library used for tasks like network analysis and monitoring. If you take a closer look at TCP structure, it plays a crucial role in dissecting network packets at the transport layer. Let's break down some of its key components, like source port, destination port. These fields represent the source and destination ports. In networking, ports help identify different services or processes. Sequence and ACK, these are acknowledgement numbers and sequence, essential for ensuring reliable data transfer. Data offset is byte indicates where data begins in the TCP packet. Flags, including fin, push, or arc, convey various control information about the packet state and purpose. Window. The window size specifies how much data can be sent before receiving an acknowledgement. The checksum. It's a checksum value used for error checking. Urgent is a field is used to indicate urgent data within the packet. Options. Here we can include various TCP options such as timestamping or window scaling. Padding can be added to align the packet structure. Now we see the base layer structure. It's a convenient utility for handling packet layers in Go. This structure provides two essential functions. Layer contents returns the raw bytes of the packet layer. It's useful when you need to access the entire packet content, including headers and data. And layer payload returns only the payload data, excluding the headers. This can be handy when you want to work specifically with the data contained within the packet. These functions simplify the process of working with network packets in Go. They abstract the complexities of packet structure, making it easier for developers to extract the information they need. Now let's explore the link layer. Specifically, let's look at the Ethernet type 2. Ethernet is like the foundation of your network, providing essential connectivity between devices like computers, routers, and switches. One of the Ethernet's key features is the use of MAC address. MAC stands for Media Access Control, and it's like a digital ID card for network interface controllers. Each network interface controller, be it the Ethernet port on your computer or a Wi-Fi card on your laptop, is assigned a unique MAC address. Now let's look at the Ethernet type 2 frame. It starts with MAC header. This header is 14 bytes long and contains vital information. It includes the destination MAC address, where the frame is headed, and the source MAC address, where it's coming from, and the ether type, indicating the protocol being used. Data section carries the actual payload, which could be anything from an IP packet to an ARP request. It ranges in size depending on the data being transmitted. Now, CRC checksum. Ethernet doesn't just send data blindly, it's thorough. So 4 byte CRC, cyclic redundancy checksum, ensures data integrity, helping to detect and correct errors in transit. These elements work together seamlessly to transport your data from one device to another. So the next time you plug into an Ethernet cable or connect to Wi-Fi, remember that there's a whole world of MAC addresses and Ethernet frames behind the scenes, making sure that your data gets to its destination safely and efficiently. Every device connected to the internet has its own unique identifier called IP address. Think of it as a digital home address for devices. IP is inherently unreliable. Packets can be dropped, reordered, duplicated, or even corrupted in transit. There are no acknowledgements provided, so you do not know what happened to the data. Also, one can arbitrarily change the source IP address. Routers don't even double check the source IP, which can open the door to potential threats like denial of service attack. Now, in transport layer, TCP and UDP are two protocols within this transport layer, and TCP or Transmission Control Protocol is the one for reliability and order. It ensures that all the data is transmitted and received in a consistent order. Applications that rely on TCP include web browsing, loading web pages with all their elements, file downloads, email transfers, and more. In a sense, TCP guarantees that no data gets lost or jumbled along the way. Unlike TCP, UDP or User Datagram Protocol doesn't worry too much about ensuring every piece of data arrives intact and in right order. It's ideal when you need real-time communication or have simple, short query response requests. UDP shines in applications like video streaming, online gaming, and voice over IP. In these cases, a few data packets lost might not matter as much, as keeping communication flowing smoothly is the importance. In summary, TCP and UDP serve different purposes in networking. TCP is go-to for reliability and order, and UDP is for simplicity and speed. The domain name system, often abbreviated as DNS, is a crucial component of the Internet's infrastructure. It serves as the digital translator, converting human-readable domain names into their corresponding IP addresses. Here's a simplified view of how it works. When you request to a website, your local DNS resolver, often provided by your ISP, forwards your request through a series of DNS servers. These servers may already have the IP address you need stored in their memory. Thanks to the mechanism of caching, caching helps speed up the resolution process by storing frequently requested domain to IP mappings for a certain period. DNS system translates the friendly website name into a IP address. This numerical language is what routers and computers use to pinpoint the location of your desired web server. DNS primarily uses UDP or User Datagram Protocol for its communication. Its lightweight and connectionless nature makes it an ideal choice for quick exchanges like DNS queries. All the best for your assignment.